The space P2 represents all second-degree polynomials. Recall that a polynomial such as p of x equals 4 plus 8x plus 1x squared would be the vector 4, 8, 1 in P2. The standard basis polynomials for this space are 1, x, and x squared. Also remember 1 would be the vector 1, 0, 0, x would be the vector 0, 1, 0, and x squared would be the vector 0, 0, 1. The function f defined by f of p of x equals the quantity x plus 8 times the derivative of p of x with respect to x is a linear transformation from P2 to P2. It takes the derivative of p of x and multiplies the result by the quantity x plus 8. We're asked to write the matrix for this linear transformation according to the standard basis polynomials, which means we want to determine the transformation matrix. Remember, we can find the transformation matrix by determining the transformations of the vectors e1 through e3, where each transformation will give us a column in the transformation matrix. So we can determine the transformation matrix if we determine where the standard basis polynomials go under this transformation. So to begin, we let p of x, the input function, be equal to the first polynomial in the standard basis for P2, which is 1. And then we determine the quantity x plus 8 times the derivative of 1. Well, the derivative of 1 is equal to 0. The quantity x plus 8 times 0 is 0. Since p of x equals 1 maps to 0, and the vector for 1 is the vector 1, 0, 0, we now know the vector 1, 0, 0, or the vector e1, maps to the 0 vector, which is the vector 0, 0, 0 into R3. This will be the first column of the transformation matrix. Next, we set p of x equal to x, the next polynomial in the standard basis for P2. And then again, we calculate the quantity x plus 8 times the derivative of x. The derivative of x is equal to 1. The quantity x plus 8 times 1 is x plus 8. So x maps to the quantity x plus 8 under this transformation. The vector for x is the vector 0, 1, 0. The vector for x plus 8, or 8 plus x, is the vector 8, 1, 0. So now we know E2 maps to the vector 8, 1, 0, which is the second column of the transformation matrix. And then finally we set p of x equal to x squared, the third polynomial in the standard basis for P2, and once again calculate the quantity x plus 8 times the derivative of x squared with respect to x. The derivative of x squared is 2x. The quantity x plus 8 times 2x is 2x squared plus 16x. Since x squared maps to 2x squared plus 16x, we know the vector 0, 0, 1 of the vector e3 maps to the vector 0, 16, 2, which is the third column of the transformation matrix. For number 2, we're asked to write the polynomial 5 plus 3x plus 6x squared as a vector, which is the vector 5, 3, 6. And then for number 3, we're asked to use the matrix from above and calculate f of the quantity 5 plus 3x plus 6x squared and write the answer as a polynomial. Well, we already know the transformation matrix A, and we know the vector form of 5 plus 3x plus 6x squared. So to find f of the quantity 5 plus 3x plus 6x squared, we just need to multiply the transformation matrix and the vector form of 5 plus 3x plus 6x squared. Multiplying, we get the column matrix or vector 24, 99, 12, which is equal to the polynomial 24 plus 99x plus 12x squared. Of course, if we did want to check this, we could set p of x equal to 5 plus 3x plus 6x squared, and then determine the product of x plus 8 and the derivative of 5 plus 3x plus 6x squared with respect to x, which I've shown below just to check, and notice how we do get the same result. I hope you found this helpful.